Hi, my name is Alan Lazarus. I'm a professor at the University of Toronto, a scientist in the Keenan Research Centre of St. Michael's Hospital, and a senior scientist with Canadian Blood Services, and this is an introductory video on antibodies. So the antibody we're showing here in the middle that looks like a oddly shaped toilet plunger is an IgG molecule, or represents an IgG molecule, also known as immunoglobulin G. And when people talk about antibodies, if they don't mention the type of antibody, they're usually talking about IgG. So let's hear a little bit more about antibodies. So all of us have antibodies in our blood and tissues. They're present at very high levels, and they help protect us from infections. Not everybody has antibodies in their blood, so patients with primary immune deficiency, as one example, don't have antibodies, and these patients can have increased chances of getting infections. So one of the treatments for people with primary immune deficiencies are getting an injection of antibodies, as shown over here, with a product called IVIG, or intravenous immune globulin, sometimes called intravenous immunoglobulin. And basically they are antibodies taken from the blood and plasma of blood donors. And when given to people with immune deficiencies, it is very helpful to prevent infections. So for most of us who have our own IgG levels, what happens? So if you have an infection with, for example, a bacteria, a virus, or a parasite, your immune system will respond. And one of the components of the immune response will be making antibodies to those foreign invaders. So for example, in this case of a virus, we can see an antibody binding to the surface of that virus. So this particular type of virus has these little antennae on their surface, or what looks like an antenna, and these antennae are important in allowing the virus to actually enter your cells. So it's not enough for a virus just to make it into our body, but it also has to have a receptor that allows it to attach and enter a cell. And sometimes antibodies can bind to these antennae and neutralize the virus. And that is one of the ways through which antibodies protect us. Antibodies are sort of more known for coating pathogens at high numbers and signaling the immune system to come and destroy the pathogen. So antibodies are not the same size as bacteria. They are thousands and thousands of times smaller. But what will happen is if you're infected with a bacteria, your immune system will probably already have antibodies that can bind to the bacteria, and will also respond to the bacteria by ramping up the production of antibodies specific for that bacteria. There are 5 major classes of antibodies in humans. The first is IgM. This is the largest antibody. As you can see, there's a lot of the suction cups on the IgM. It's made relatively quickly in the immune response after a few days, but it is not the greatest antibody from its ability to bind to the pathogen, and that's partly because it appears so quickly. So the IgM does have a lot of these suction cups to sort of make up for the fact that it's a low affinity antibody, that it's not really the greatest in the world, and that's IgM. IgG, which is the major class of antibody and the most abundant antibody in the blood, is shown here in the middle. So an IgG molecule, what it does is it takes a little longer to appear, but it's higher activity and higher affinity than the IgM, and it is the major antibody that helps protect us against most infections. Then there's IgA. IgA is particularly predominant in the gut and helps us protect us from bacterial infections in the gut. There's also IgE. IgE helps protect us against parasites, but it's probably more known for its role in allergy, and IgE is therefore the antibody that can cause allergy. And then finally, there's IgD, which has really not been all that well studied yet. We're just starting to learn about IgD, and we won't talk about it in this video. So what happens when you get a bacterial infection? Are the antibodies all the same? How does it work from a specificity point of view? So there are two major components to the antibody that we consider. First is the constant region. So the constant region is basically the same for all antibodies of a given class and doesn't really change very much over the course of an immune response. There's a few sugars on the constant region that can change and affect some of the properties of an antibody, but for the most part we can consider it as being constant. Then there's the variable region, which some would say is the exciting part of the antibody. That's the part that binds the foreign pathogen. So think of having millions and millions and millions, tens of millions of antibodies, such as IgG molecules floating throughout your body, each with a different variable region. So the idea is when you get an infection with a virus or a bacteria, your immune system will find one antibody or a few antibodies that will be able to bind to and mark that bacteria for destruction. So how does it work? So here we have a bacteria on the bottom with three of these little triangles that's meant to represent some wacky thing that's on the outside of the bacteria. And we have a selection of antibodies on the top. And what you can see is that one of these would be a fairly good match for the bacteria. And so the idea is whether it's an initial IgM that's binding to the bacteria or IgG, it will bind and signal the bacteria for destruction. One of the wonderful things about the immune system, IgG, is its ability to sort of mature and actually get better over time. So the initial antibody response might be this antibody that doesn't bind all that well, but over time your immune system will start to produce antibodies that are a better fit for that bacteria and have a much better chance of inactivating or destroying that bacteria. So the final phase is the destruction of the bacteria, and that is usually performed by the macrophage. There are a number of other mechanisms that can be used, but what happens is when you get several thousand antibody molecules binding to the bacteria, receptors on the macrophage will recognize the handle portion of the bacteria, bind it, and engulf that bacteria and actually swallow it up in a process called phagocytosis. And that destroys the bacteria. The bacteria enters the macrophage fires many different toxic molecules at the bacteria inside and gobbles it up, and usually that works. So that's the end of this video. If you like it, give us a like and we might make more. Bye.